This video is going to be all about learning some information about the original function if perhaps we can't find an antiderivative. Now I'm going to give you a function that we can find an antiderivative, and we're going to just play around with that just to see how it all plays out. But this is a way to just kind of estimate some things. So first of all, let's talk about slope fields. Back in the day, when you were first learning about derivatives, I would give you a function like this. And if I call this one f of x, then I would ask you to draw the derivative of this function. And the way we would draw the derivative is by looking at all of these tangent lines. And from those tangent lines, then we could figure out what the derivative graph would look like. Well, that's a horrible straight line. And so we can see that the slopes are negative, the slope is 0 here, and then the slopes turn to positive. So based off of what we've known and seen and done, this would be a linear equation. Okay, so that was the derivative. So what we're going to do, what slope fields does, is it works backwards. It says, here are all these tangent lines. What is the original function going to look like? So it's a little bit tedious, but it's going to work. I'm going to show you how we work on slope fields. So if we're given this function dy over dx, so the derivative is 2 times x times y. And you and I, because your skills are so amazing now, you can find that antiderivative. But let's just say it were a function where you couldn't. So what we're saying is we know the slopes, or at least we can find the slopes. So if we graph those slopes, that's going to give us an idea about the shape of the original function. So this is really tedious and not the best, and this is an estimate, so it's not going to be perfect, and nobody expects it to be perfect, but what we do expect is that you are relatively close, at least mostly close. So we're going to set up a table here where we're going to plug the x and the y values, or we're going to find an x and a y value, and we're going to use that x and y value to figure out the slope of the tangent line, or the derivative. Now, if we're looking at a graph, most of the time when you're doing a slope field like this, the points where you're trying to find the slope are given to you. But for our case, I'm not going to give you which points, but typically if it just says draw a slope field, I try to do as many points as I can. I'll show you what all of this means. Just go along with me for now. I'm leaving a little space, so we've got a little room here. Don't forget to look at values along the axis. Don't forget to look at values at the origin. So all of these points, don't forget to look at points in each quadrant. And eventually this will get faster and you'll get better at it. You'll see patterns, and those patterns, oops, that one shouldn't be there. And these patterns will hold in, it's best to kind of see what's going on. All right, so I probably should have set this up first so I wasn't wasting your valuable time setting up dots on the graph. But what we're going to do is just start with one point, and we're going to find the slope at that point. So I'm going to start with the point 0, 0. Why not? If I plug 0, 0 into this derivative graph, then the slope is 2 times 0 times 0. So we know we have a 0 slope here at the origin. A 0 slope could mean there's a minimum, could mean there's a maximum. All we know is that there's a 0 slope. So let's keep looking. Now, what if we look at the point at 1, 0? So when x is 1, y is 0, that's 2 times 1 times 0. Slope is still 0. And then if we're at the point 2, 0, the slope is 0, slope is 0. So see, this is what I mean by patterns. We don't have to actually put all of these values in the chart, because once we notice a pattern, we know some things are going on here. All right, let's look at some other points on the axis then. Let's look at the point 0, 1. So if x is 0 and y is 1, that's 2 times 0 times 1. Slope is still 0. So anywhere that y or x is 0, the slope will be 0. So this is looking a little funny. Let's keep going. Now let's try another point. Let's try at the point 1, 1. So if x is 1 and y is 1, the slope is going to be 2. Now here comes the estimation. We're going to draw a little tangent line at that point 1, 1 that has a slope of 2. I know that if I'm at this 45-degree angle, I know that that slope's 1. So I know I need to go a little steeper than that. How steep? Steeper than 1. It's all relative. It's all relative. And I know this is hard to swallow, but you have to understand that we're just getting the general shape. Okay, so I did 1, 1. Now let's look at the point 1, 2. So that's 2 times 1 times 2. That slope is 4. And this gets steeper. And then 2 times 1 times 3 will be even steeper, all relative to what you started with. We're not looking for specifics. Okay, I want you to pause and I want you to finish graphing this slope field. So go do that, pause this, and then come back. Okay, welcome back. So now I'm going to finish this. I wish there was a way to pause my recording, but I can't, but I'll mark it on the YouTube so you can just fast forward to the finish. So if I'm going to look at this point 2, 1, then it's going to be the same outcome as before. It's 2 times 2 times 1. So that slope is 4. So I need to make this slope 4, so it needs to be kind of steep, about the same steep as the other one. And then 2 times 2 times 2, this one's going to be really steep. We're just seeing that it's getting steeper. And if I look in the negative, so if I do the point 1, -1, I have 2 times 1 times -1, so that's -2 for the slope. So that means it's going to be a little steeper than -1, but in the negative direction. So like this, and then steeper and steeper. And then 1 times -2 would be -4, so it's even steeper than that, and steeper and steeper. Okay, I'm going to stop here because this is going to give me enough of an idea. Actually, maybe let me put another one on the other side. So if I do the point -1, 1, also -2. These are all negative. Now back down in the third quadrant, both values are negative. So if I have the point -1, -1, 2 times -1 times -1, that's +2. So the slopes are positive again. Okay, now from here, sometimes, and you should fill in the dots to get a better picture, but I'm not going to continue going on with this. You should fill in the dots to continue the picture to kind of get an idea. So what I can say though is at these values along the y-axis, these values here, I notice that the slope to the left, if we're above the x-axis, the slope to the left is negative and the slope to the right is positive. So that would mean that those values above the x-axis would be relative mins. However, if I look on the right, or below the x-axis, I see the slopes on the left are positive, the slopes on the right are negative, so those values along the y-axis are relative maxima. And so this graph is just giving me a little bit of information. Even though I don't know exactly what the graph looks like, I can see the pattern going on. I can see that we probably have a min or a max here. So now let's go take a look at some questions that you might see on an FRQ. So let's just say if you've given this differential equation, the question will be, find the particular solution. You've seen this before. Find the particular solution. Y equals f of x, so in other words, get y by itself, to the given differential equation with the initial condition f of 0 equals 2. Okay, so you've done this before. This was on your last test. All of that is to say, isolate y. Find the y value, find c, or find y, isolate y, and find c. So given this function here, we're going to separate the variables. Dy equals 2xy dx. Divide the y out to the other side. Dy over y equals 2x dx. Now that we've separated the variables, I know this is the natural log of y. This is x squared plus c. Y is equal to e to the x squared plus c. So y is equal to, well, let's find, sorry, I should have done this a little bit earlier. Let's find that c value. I got a little ahead of myself. Let's find that value of c right now at this step before we do anything else, just so you don't make any mistakes. So we know that y is 2 when x is 0. So I know that c is the natural log of 2. So I end up with the natural log of y equals x squared plus the natural log of 2. Okay, so then we found the particular solution, but now we have to satisfy this part where we isolate y. So I'm going to go back and do that. So we're going to say that y is equal to e to the x squared plus the natural log of 2. Y is equal to e to the x squared times e to the natural log of 2. Y equals e to the x squared, x squared, and e to the natural log of 2 is just 2. So here is the particular solution to our differential equation. Y equals 2e to the x squared. Let's go see what that graph looks like and see how that might show up in this slope field. So let's go look at 2e to the x squared. I'm going to do that in Desmos. I'm going to let Desmos open. So I've got y equals 2e to the power of x squared. So there's our graph. Kind of parabolic looking, interestingly enough. And that's exactly what our graph was starting to look like. It was starting to look a little parabolic. Now, depends on which point we're going through. In this case, I mean, that's where that natural or that absolute value comes in. Because if we've got the absolute value of y, that means we're only looking at the values above the x-axis. So all of this stuff below, if this were on an FRQ, would not have been there because we're talking about the absolute value of y when we're integrating. So we're only looking at the values above the x-axis. And since it went through the point 0, 2, that means that we would have drawn the graph through that point, and we'd follow these lines, and I can see that it's a minimum, and then follow those curves. So I'm going to follow those tangent lines and draw my graph, and that's what it looked like. Okay, those are slope fields. A little imprecise, but still gives you a general idea of what this is going to be like.